Greetings, aspiring scientists. Welcome to my video today on Hess's law. I think this is quite a difficult topic. I did include it on my list of most difficult IB chemistry SL topics, top 10 or whatever, if you have watched that. But I do think this is one of the most difficult topics for both SL and HL for reasons that we will see soon. You need some new techniques. But let's go through it slowly and with some examples. So let's go to my slides. We're now in 1.2.2 of reactivity, the later half of IB chemistry SL. So last time we looked at bond enthalpies, how to find the enthalpy of a reaction from that. So Hess's law, what is this exactly? It's a translation of the law of conservation of energy from physics into chemistry. And this is kind of my own take on the definition. I don't think this is a real quote from anywhere, but the enthalpy change between an initial and a final configuration of atoms is independent of the route they take for the rearrangement. So I did explain this a little in my general video on thermodynamics a couple weeks ago, but basically, we can rearrange atoms and go through many different arrangements, but different arrangements, once they are complete, have a certain energy, right? They exist on a potential energy scale. So it doesn't matter whether you go from point A to B directly, or if you take a side route to C and then go to B, or CD, CDE, whatever, if you go through multiple steps. As long as you finish at point A and point B, you know the energy difference between those configurations is always the same. That's kind of Hess's law in a nutshell. So this means that enthalpy is a state function. I've explained that in a previous video, like gravity from physics. In the room that you're in, there's like a gravity field, right? At any particular height, something has a set energy. It doesn't matter what path it takes to get to any certain height. If you know something is on the table and something's on the floor, you know the potential energy difference between them. That's just what a state function means, and enthalpy is one of those. So if you change from one point, the reactants, to another point, the products, a set amount of energy transfer is required. It does not depend on the path. So we'll see kind of what this means mathematically very soon. So we'll have something like this. Just look at a general example first. If we have reactants, they can go to intermediates, B, or they can go to products, the final state, C. If they go directly to final products, they'll take pathway X. This is delta H1. It's a direct route. But of course, there are many reactions that have alternate pathways with intermediates. So you can go step 1 and step 2 instead of the direct path, delta H2 and delta H3. That's process Y and process Z. But process Z ends on the same place as process X, the products, the final state. So we can say we know that delta HX, delta H1 is equal to delta HY plus delta HZ. You can either go the direct path or multiple steps in a different direction. But if you finish with the product C, you can say this, delta HX equals delta HY plus delta HZ. And you might be able to solve for some unknowns if you have enough information. So here's a maybe real example with sulfur and sulfur oxides. So if the product we'll be forming is SO3, sulfur trioxide gas, you could immediately just combust some sulfur and add 1.5 mole of O2 gas to 1 mole of sulfur and go right to the products. But oftentimes this is done in 2 steps. Instead, we'll add 1 mole of O2 to make sulfur dioxide first. That's an intermediate pathway to make intermediate B, SO2. But the reaction is then maybe not done, not stable yet. So we add another 0.5 mole of O2. That's process Z here, or delta H3. And once that's done, you end up with SO3 again. So whichever path you take, the direct or the intermediate alternate pathway, we can say that delta Hx equals delta Hy plus delta Hz. We don't have any real numbers for these in this case, but we'll show some examples soon that do have real numbers. So this is a fairly simple example, and you can see in any case, you're going to be adding 1.5 mole of oxygen to your sulfur. It's just, do you do it all at once, or do you do it in 2 steps? Okay, so here, maybe a real example with real numbers. Using Hess's law, calculate the enthalpy change of the following reaction. Carbon plus 2 moles of H2 plus 0.5 mole of O2 goes to 1 mole of methanol, CH3OH, liquid. Delta H is what? And then we get some useful equations. So we've got combustion of methanol. So methanol plus 1.5 mole O2 goes to CO2 plus 2 H2O, delta H minus 726 kilojoule per mole for that. We've also got the combustion of carbon, or the enthalpy of formation for CO2. That's, both of those are this equation, minus 394. And then H2 plus O2, this is combustion of H2 gas, or the enthalpy of formation of water, delta H minus 286. Okay, so I'm going to show you some cool tricks to figure this out. There's actually multiple methods to do these, but one of the methods is to try to add up several equations until the results of adding those equations equals your target equation. So our target equation, we want to know delta H unknown of this at the top. So you've got to try to make this equation from the other 3 equations that we are given here. If you've never done this before, it can be a little bit weird, but I'll go through my thinking process here. Okay, so we need to build this equation at the top in the yellow circle. That means we need a methanol, CH3OH, on the right side as a product. None of our 3 equations underneath has methanol as a product. In fact, only one of these equations even has methanol at all. It's the first one there. Maybe we'll label that number 1. Okay. But what we could do is reverse this equation. If we do the opposite of this equation, instead we would take CO2 and H2O and produce methanol and O2. Doesn't seem like a very spontaneous or thermodynamically favored process, and that's right, but you can still force it to do that, in theory. So let's take equation 1 and multiply by minus 1. This is kind of like reversing it, but not changing any of the coefficients. If we do that, we will get CO2 plus 2H2O goes to CH3OH plus 1.5 O2 gas. Okay, I'm not going to write all the state symbols here again because we're just focusing on the compounds and the mole ratios here. Okay, so multiply by minus 1, that's reverse this, and that means that delta H of that will be 726, but when you reverse that process, the enthalpy switches the sign, because then it becomes a very endothermic process instead of exothermic to try to reverse this. So delta H equals 726, positive number. Okay, so what next? If we look at what else we need a bunch of carbons on the left side as a reactant in our final target equation in yellow here. So if I take my second equation, maybe I will label this number 2. This has a carbon in it, and it's 1 carbon, that is what I want. So why not just take this as it is, carbon plus O2 goes to CO2. No need to multiply or reverse anything. Delta H for this stays the same, minus 394. Okay, so just to be very clear, we're taking equation number 2, multiplying by 1. All right, so throw that into the mix that we're going to add together. Then we need some hydrogens. We need 2 hydrogens in the final equation. Our equation number 3 here has hydrogen, but only 1. So if we're gonna make that final equation, we need to double that whole equation. No reason that we can't do that though when we add these together. So we'll take equation 3, just multiply by 2. No need to reverse it. So we'll get then 2H2 plus 1O2. 1/2 times 2 is 1, and then 2H2O. And delta H for that needs to be doubled. So we'll have like 2 times minus 286. Okay. So we've got that. Now what I want to do is take these equations that I just made and add them together. This should give me my target equation, but you got to be a little bit careful how you do this. So there's a couple different ways you could show this, but I will just write basically everything that we have. So CO2 plus 2H2O plus C plus O2, and we will have 2 O2s, right? One from the middle, one from the bottom. So 2 O2 and 2 H2. Is that everything? Yep. So this will go to the product CH3OH plus 1.5 O2 plus CO2 plus 2H2O. Okay, now I need to think a little bit about what this means. So we've just added all the reactants and products together, but consider CO2, the first one. Some of it will be used up, apparently, but some of it will be produced, and in fact, equal amounts. 1 molecule or 1 mole is used up, 1 is produced. But what our chemical equations usually show us is what is changing, what is disappearing or what is appearing. What is disappearing from reagents, what is appearing in the products. You probably realize this, like when you show equations that are done in aqueous solution, you don't write H2O, even though it's floating around everywhere in your container, because it doesn't actually change its concentrations or amounts. It's not really participating in the reaction, and that's kind of what CO2 is doing here. It's maybe getting used up, maybe getting produced, but in the same amounts, so you wouldn't even notice. So when you have something in equal amounts on the left and right side of an equation like this, you don't actually even need to include it in your final written balanced equation, because it's not changing, neither appearing nor disappearing. You'll notice there's the same thing for water here. We would use 2 molecules or 2 moles, and we would produce 2. That's the same as no change. So if we then clean that up a little bit, carbon plus 2O2 plus 2H2 goes to CH3OH plus 1.5 O2. Now here's maybe the trickiest part, which is that we have oxygen on the left and right side. Generally, that's also something that you can simplify, but this time it's not the same amounts, so you can't just cross it out and eliminate it. We've got 2 on the left and 1.5 on the right. So what's the difference between the reactants and the products? What will the actual change be? If 2 moles are used and 1.5 is produced, then really you're only using 0.5. So it's the same thing as having 0.5 mole of O2 being used up in the reactants, and then nothing appearing on the product side. Because overall, the net change is just, it's getting used up as this process moves forward. And then if you look at that, that is the same as our target equation. Very nice. So that means that our original operations, multiplying equation 1 by -1, not changing number 2, and then multiplying equation 3 by 2 was correct. And that means you can just add the enthalpies together that you wrote there. So if I take all of these enthalpies and just add them together, I'll do it at the top here. So delta H unknown is equal to plus 726 minus 394, and then plus 2 times minus 286, and we will get minus 240 kilojoule per mole. And you can go check like the enthalpy of formation for methanol in some data table, and I think you'll get a number around this. So it is exothermic in the 200, 250 kind of range. So that would be a good way to solve this problem and to prove it by adding several equations together, just how we saw, like, if we treat this target equation as the direct pathway and these other 3 as indirect steps, well, it must be true that the direct pathway is equal to all the indirect steps added together. But you still need the right amount of like mole ratios and amounts of molecules of products and reactants that are reacting together to make this work. That's why we had to do all that work on the right side to really prove it. So you can imagine if you're writing an exam and you're confident that you chose the correct operations, like -1 times 2 times 1, whatever, you wouldn't have to necessarily add all these equations together and cancel out the things on the left and right sides. But I recommend that you do, because it's very easy to go on the wrong path or make a mistake if you don't add these together correctly. But if you're really rushing and you've got a lot of practice, you're confident you did it right, you could just operate or take the operations on these enthalpies instead and go straight to the last step there. Okay, let's move on. So there exists this thing called the triangle diagram or the cycle diagram, enthalpy cycle diagram for showing these kind of pathways. So we have the direct path on the top, carbon plus 2 moles of H2 plus 1/2 O2 goes to C3OH, the exact same target equation I had on the previous slide. So overall, we are adding 1 mole of oxygen to the carbon and hydrogen atoms here. We combine them into methanol, and 1 mole of O is added. or 1/2 a mole of O2, in other words. But if you check the alternate pathways, first you could combust carbon and combust hydrogen separately to make CO2 and H2O. In that case, you're adding 4 moles of O, 1 O2 to each case. That's 4 O's in total. And then if you want to go to methanol from there, you need to remove several oxygens. You need to remove 3 moles of O, or 1.5 moles of O2, same thing. And doing that, you'll end up with the same kind of process as the direct process, right? You add 4 on the left side and you subtract 3 on the right side. The total result there is you've added 1 mole of oxygen to your carbon and hydrogen. So the net, or the resulting moles of oxygen atoms added, is the same regardless of the pathway that you choose, whether it's direct path on the top or the 3 separate steps on the bottom. You get to the same place, methanol. So the process enthalpy on the top must be equal to each of the enthalpies on the bottom here, the 3 added together, just like we showed. So this is kind of another method that you can use to prove and add up enthalpies. However, I must say that I really don't prefer to use these cycle diagrams, and my students don't usually either. Maybe it's just because I'm not good at explaining it that well. But most of them prefer to add up the equations as I did on the previous slide, if they have the choice. But you don't always have the choice. Some questions ask you to make this cycle diagram or to use one that's given to you. So you need to know both kind of methods. All right, and this is just showing the exact same equation again, but with the enthalpy numbers, and showing how you can take a shortcut here. If you've drawn this cycle diagram properly and everything balances out, you can use this to calculate the answer for the enthalpy of the target reaction on the top. So if you combust carbon, it's exothermic, minus 394. You'll also be combusting hydrogen. So you kind of put these together, minus 394 plus 2 times minus 286. And then the combustion of methanol is minus 726. But that arrow also must sort of go in the same direction as the combustion of carbon and hydrogen. You can kind of imagine this cycle diagram as having an energy scale. Potential energy here on the left side. So if we go downwards with a downward arrow, that means our products there are more stable and we'd be releasing energy exothermically to do so. So combusting methanol is also exothermic, minus 726. But if we combust carbon and hydrogen and go down to that low point here, the target equation requires us to go back up to methanol. That means we would draw an arrow kind of in the opposite direction of what is initially shown in the diagram here. So instead of minus 726, we have to change the sign to a plus. That's why it shows up as plus 726 in my little equation here on the right. So combust carbon, combust hydrogen, minus 394 plus 2 times minus 286, and then inverse combust back to methanol instead through that right side pathway. That's going to be plus 726. Reverse the sign of that arrow, reverse the sign of that enthalpy value. And you get the same answer then, minus 240. So sometimes this can work well, especially for combustions like this and enthalpies of formation. But other reactions can make this very, very complicated because although we've drawn kind of an energy scale on the left here, these arrows are not scaled appropriately. Like, look, the arrow for minus 286 is the same size as minus 726. So when things get any more complicated than this, it starts to not make a lot of sense, and it starts to become, in my opinion, impossible to draw a triangle to actually solve these. I'm sure we'll see an example of that later because I've prepared one. But just some things to consider. Okay. Another practice then, determine the enthalpy of formation of ethane, C2H6, using enthalpy of combustion data from the data book in section 14. Okay, so there might be multiple methods for finding the enthalpy of formation from ethane, including just looking it up in a separate section of the data book. But this says calculate it from combustion data section 14. That means we must do that. So we need to know, again, the definition of enthalpy of formation of ethane. That means creating it from base elements. So we would create it from some carbon and some hydrogen. But these elements need to be in their standard states. So we would have solid carbon, and we would have H2 gas. That's its standard state. Add these together, and we will make C2H6, also a gas. Now balance this. We need at least 2 carbon atoms from the solid phase, and we have H6 on the right, so we would need 3 H2s. And then we can make this C2H6 gas. And that's what we're asked to find. What is this enthalpy? Using enthalpy of combustion data. So all the enthalpy of combustion data in section 14 is associated with a chemical equation as well, right? What is it associated with? Well, what combustion can we use? We can use the combustion of carbon and the combustion of hydrogen. So if we label in equation 1 here, the combustion of carbon, this will be carbon plus O2, carbon solid plus O2 gas goes to CO2 gas. That delta H is in the book. It's minus 394. Then the combustion of hydrogen, that's going to be H2 plus O2 goes to H2O. Gas, liquid, gas, but we only need 1/2, or 0.5 moles of O2. Delta H for that process is minus 286. Okay, so we can see we have a good start here, but we need C2H6 in an equation as well. So there is the combustion of that as well. We can label that equation 3. Combusts ethane, C2H6 gas, plus O2 goes to CO2 and water. And then balance this. So we'll need at least 2 CO2. We'll need 3 H2O for those H6. And then O2 needs to be 7/2 to get these 7 O's required. And delta H for that process from section 14 is minus 1,561 kilojoule per mole. Okay, then we can start trying to add these equations 1, 2, and 3 together to get the target equation on the top. Reminder, we're trying to build this. So we're going to need, I think, double equation number 1. We're going to need triple equation number 2 to get those hydrogens. And we're going to need the inverse of equation number 3. So I'll write those quickly and then try to add them up. So if 1 is doubled, we'll get 2C plus 2O2 goes to 2 CO2. If we triple number 2, we'll get 3H2 plus 3 over 2 O2, or otherwise known as 1.5. Go to 3H2O. And then if we reverse equation 3, we'll get 2 CO2 plus 3H2O goes to C2H6 plus 7 over 2 O2. Okay, so then we want to add these up. When we add these all together, what's it going to look like? I'll try to draw it over here. What can we cancel out though? So we will have 2 carbon dioxides on the left and 2 on the right products. So essentially no change there. We've got 3 waters, 3H2O that will be used and 3 produced. No need to write that. But we're going to have 2 carbons, 3 H2s, some oxygens. How much though? We've got 2 O2 plus 3 over 2 O2. That is essentially 7 over 2. If you consider that 2 is the same thing as 4 over 2, we have essentially 4 over 2 plus 3 over 2. That equals 7 over 2. So luckily that turns out it's exactly how much we have produced in the products as well. We use up 7 over 2 O2 and we produce 7 over 2. So these oxygens will all cancel out. So the only product we actually have is the C2H6. And that is the target equation. Formation of ethane. So that means these multipliers I chose were correct. So you just need to add all those numbers together. I'll try to do it here on the right. So this delta H is equal to double number 1, 2 times minus 394, triple number 2, minus 286, and then inverting or switching the sign on number 3. So this is plus 1561. Okay, so all that comes out to a number minus 85. So still exothermic, minus 85 kilojoule per mole. And you can go check in the data book other sections if the enthalpy of formation of ethane is like this, and I think it is minus 85, minus 86-ish. So this worked out. But this is how you would solve this, by using enthalpy of combustion data to find the enthalpy of formation of ethane. More likely on an exam, they'll ask you to find something that you can't check so easily, so you got to practice this first with some ones that you can check the answer and make sure you're doing it correctly. Okay, good practice. Next. Okay, another practice, calculate the enthalpy change of the reaction below using enthalpy of combustion data that is given. So if it says use the data given, don't go to your data book for those, just use what's on the page given to you. So this is the enthalpy of formation of ethanol. So what could this delta H be? Well, we need to add the equations below. If we label these number 1, 2, and 3, try to find some combination and multipliers of these that would work. I think I'm not going to go through the whole adding the equations together because I don't have space on this slide, but you can see that we're going to have to take equation 1 and invert it times -1. How about number 2? We're going to need to double that. We need 2 carbons. And how about number 3? We're going to need to triple that. We need 3 H2s. And doing that should cancel out all the compounds correctly to give you the target equation on the top. 3H2 plus 2C plus 0.502 goes to C2H5OH. Okay, you can try that yourself, but if we just use these multipliers for the numbers, I have checked it myself, it does work. So if we invert number 1, we're going to have plus 1367. If we double number 2, we're going to have 2 times minus 394. And if we triple the third equation, we're going to have 3 times minus 286. And that comes out to minus 279, which is close to the enthalpy of formation for methanol. Minus 279 kilojoule per mole. That's the answer through this method and these numbers. Again, different sources you check might have slightly different values for this enthalpy of formation for methanol, just because here we're only using whole numbers and like 3 or 4 sig figs. But it's possible to do this with more and get slightly different answers. Okay, good. I think I have one more pretty challenging one. Yes, so determine the enthalpy change for the reaction below using the reaction data provided. Then construct an enthalpy cycle diagram. This is a real question from a textbook, Oxford Course Companion. So 4 NH3 gas goes plus 5 O2 gas goes to 4 NO plus 6 H2O liquid. That's the target. And what we have to work with is N2 plus O2 goes to 2 NO plus 66. N2 plus 3H2 goes to 2NH3 minus 92. And 2H2 plus O2 goes to 2H2O minus 572. Okay, and we need to find what is this delta H. So first, we'll just try the quickest method. If you would try to add equation 1, 2, and 3 together through some combinations and inversions, what could you do? Well, I would recommend you take equation 1, double that, because we have 4 NO in the products of the target and 2 NO in the products of this one, so we could double that. Take equation 2 and invert and double it times minus 2. Why would we do that? Well, we need ammonia, NH3, on the left side, so we have to invert equation 2. But we also need to double it because we need 4 NH3 in the target equation, so invert and double equation 2. Equation 3 then, triple that. Equation 3 times 3, because we need 6 H2O, and we have only 2 H2O in that equation. That's the only equation that has any H2O. So we absolutely have to triple equation number 3. So if we do that, you can check, but adding together those equations after multiplying by those factors will give you the target equation. So we get 2 times 66 minus 2 times minus 92, and then 3 times minus 572. All of these added together will give you about minus 1400 kilojoule per mole. So that's what this enthalpy of the target is, minus 1400. Okay. So it's a little bit tricky to sort of see what you need to be prioritizing in these three equations. But if you look, equation 1 is the only one with NO, so you've got to get the right number of NO from equation 1. That means you double it. Second equation is the only one with NH3, so you've got to reverse it and double that as well to get 4 on the left side. And equation 3 is the only one with H2O. So you got to look at what equations are the only ones that have some of the target compounds in the target balanced chemical equation. Okay, excuse me. Now, the difficult part, construct an enthalpy cycle diagram. I have tried to draw a triangle cycle diagram for this. I was not able to do so in a way that made any sense. So I looked up the answer guide. The answer guide explains how you would draw it with words, but doesn't actually draw it or show you. And even from that, I was not able to draw one that made any sense to me. So I don't think it's possible. I don't think it's possible to draw these equations in a triangle form that makes any sense, with like an energy profile that goes up and down the page. Didn't make any sense to me, but there is a way to draw a cycle diagram. I don't think you would be asked this on an SL exam, but I want to show you anyway, just to prove that it's possible. What I would recommend is that you draw something called a Born-Haber diagram. A Born-Haber diagram is like a cycle diagram, but everything is scaled properly. The y-axis of an energy potential does mean something, and the positions of the arrows and these components, these compounds, does have a strict kind of meaning on the scale. So I'll try to show you how to draw that, but it's a bit of a ride, so buckle in. I'm just going to exit this and go to a full whiteboard so I have a full space to work with. Okay, here we are on the whiteboard. So I want to remind you what our target equation was. 4NH3 plus 5O2 goes to 4NO plus 6H2O. And then quickly, our equation 1, 2, 3, N2 plus O2 goes to 2NO. N2 plus 3H2 goes to 2NH3. And 2H2 plus O2 goes to 2H2O. So we need a way to get all of these on an energy scale with positions and arrows with directions and magnitudes that make sense. That's what's known as a Born-Haber diagram. It's an HL topic. So SL students, you would not need to draw this. But HL students, this is very good practice for you to do and check your understanding. So where to begin? Well, draw your scale. We have this potential energy scale, and we're going to obey this. Up is more energy, down is less. And we're not going to draw any diagonal arrows. Now, let's start with the target equation. We know that that was exothermic, that was delta H minus 1400 that we calculated. That's quite exothermic, so that's going to be a big down arrow. So maybe I'll start 4NH3 plus 5O2. Oops. Plus 5O2. exothermically releases minus 1400 kilojoule per mole. And that will leave us with some products, 4NO plus 6H2O. So I'd recommend you start there. What you do next, though, is really not always obvious. But what I like to do is ask, is there anything that is higher energy and anything that is lower energy in any of the other equations? And then you can draw those above or below. So I'll remind you the enthalpies for 1, 2, and 3 as well. So do we think there's anything here that's lower energy than 4NO plus 6H2O? Well, if you look at equation number 1, this says N2 plus O2 goes to 2NO endothermic. That means NO is above nitrogen and oxygen gas in terms of energy, because it's endothermic to even produce that. So somewhere underneath here, you've got to have N2 plus O2, and that process is endothermic plus 66 to make 4NO. Now the weird thing here is that I want to keep everything I'm working with here basically included in all of the equations I'm going to write. So I'm going to include 6H2O here. Because it appears in the middle version here, plus 6H2O, but if we just keep it the same, it's not included in this plus 66 enthalpy value, because there's no change to the H2O. But to make 4NO, I'm actually going to need 4 nitrogens and 4 oxygens, so 2 of each of these. And that means my plus 66 from my equation 2 at the top needs to be doubled to really make this jump. Okay, plus 66 times 2 to make 4 moles of NO. So it's looking like probably the lowest energy, most stable form of all the atoms in this process is 4N2 plus 2O2 and 6H2O. Okay, now is there anything higher energy than 4NH3 plus 5O2? Well, yes, I do believe there is. What about N2 and O2 with just H2 gas? We have a process which makes ammonia from H2 and N2, which is exothermic, minus 92. Now you'll notice it doesn't include oxygen. So if we add some numbers here, how much N2 do we need to make 4NH3? We need 4 N's, so double N2. And how much oxygen will we need to get to that step underneath? We're not actually using oxygen in the ammonia equation, so just keep it as 5. That way there'll be no change to the oxygen, the O2, which is what we want if we're doing equation number 2, right? There's no oxygen included in that. But we have doubled this from the original equation, so minus 92 times 2, in order to go down that step. Now there is another pathway here to get down to the bottom, and it's one of our equations, I think the bottom one. If you combust H2, oh, sorry, one thing I realized, we didn't have enough hydrogen here. We need 6 of this to make 4NH3. Okay, now if we combust oxygen and hydrogen together, that's going to be very exothermic, and I just won't touch the nitrogen, but that's another way to take this all the way down to the state that we have at the bottom here. Combust oxygen and hydrogen together to make H2O. But I'm not going to combust all that oxygen. I'm only going to combust 3 moles of it, so that 2 moles are still remaining to make this cycle complete. So 2 moles of H2 plus O2, that's our equation number 3, goes to 2H2O. That process is minus 572. But how many times are we going to have to do that? We're going to make 6 H2O, right? So we're going to need to triple that value, which is why this arrow is so big and so exothermic. All right, so I'm actually just going to calculate some of these numbers. So 1400 is fine the way it is. Minus 92 times 2. This is equal to minus 184. Plus 66 times 2. This is equal to plus 132. Minus 572 times 3. This is equal to minus 1,716. All these are in kilojoules per mole. I'm just not going to write those units on every single number here. So that's very difficult, right? I think most people would not know where to start or where to go if they choose a starting point. But I hope you can see that what I've written here makes a lot of sense. It's a complete cycle where there's like 2 pathways, right? There's on the left side 1 big direct path to combust oxygen and hydrogen and get some water. And then on the right side, there's another pathway where you can change hydrogen and nitrogen into ammonia. You can change oxygen and ammonia into NO and water. And then you could change NO and water into N2O2 and H2O by going down all the way to the bottom. And what you'll find is that the height of this right side, the whole height of this diagram, which must be 184 plus 1400 plus 132. When you're considering the height, you don't need to consider the signs or the directions of the arrows. It ends up being 1,716 height units of energy, which is the exact same height as the left side, which is just 1 direct pathway, exothermic, minus 1,716 down to the bottom. But I had to include these multipliers of triple the left side, double some of these values in order to make the actual numbers of atoms work out to be like conservation of matter, right? We can't have things disappear or appear anywhere. So that's very difficult. That's like advanced Born-Haber diagram HL stuff, but it's the only way I see to draw a enthalpy cycle diagram for this last question that makes any sense at all. And this version makes a lot of sense to me. I hope it makes some sense to you. This is how Born-Haber diagrams work. Okay, and that's all I have for today. Next time, I think we'll get into fuels, especially combustion, the beginning of the fuels topic. Hope you learned something. Have a good one. See you next time. Bye-bye.